Alright, I was asked to do a little video on some of this organic chemistry that we're working on, dealing with, and figure I'll just throw them all into one kind of short video here that will cover a lot of the application stuff that we've done here in class. One of the things we've been learning to apply is the general formula. So when you're dealing with an alkane, it's going to fit the general formula CnH2n plus 2. In other words, the number of hydrogens will be 2 times the carbon plus 2. So if I say you have a 4-carbon alkane, the number of hydrogens will be 2 times 4 plus 2. So 2 times 4 is 8 plus 2 is 10. There'd be 10 hydrogens in that particular molecule. For the alkenes, and again, we're only working with alkenes that have one double bond in them. The formula is CnH2n. We effectively lose 2 hydrogens because of that double bond, so the plus 2 part disappears. So if I say write a molecular formula for 4-carbon alkene, let's see, 4. For the hydrogens, it'll be 2 times 4. It'll be 8. And finally, for the alkynes, these will have one triple bond in it, and only one triple bond. The formula is CnH2n minus 2. So again, I ask you to do one for a 4-carbon alkyne. We're going to do 2 times 4 minus 2. 2 times 4 is 8, minus 2 is 6. Again, that's one way that we can apply these general formulas. The other way we can apply these general formulas is in a situation where I give you the formula and I ask you what it is. So I give you C7H12. And I ask you, is this an alkane, or an alkyne? What you have to do is figure out what pattern that 12 fits into. 2n plus 2, 2 times 7 is 14, plus 2 is 16, would be the alkane. 2 times 7, or 14 in this case, would be the alkene. 2 times 7 minus 2, or 12, would be an alkyne. That formula is for an alkyne. You can run through all 3 equations and see which one it matches. Or one of the things I suggested you to do is focus in on the alkene equation, the one that's in the middle. So let's say we have C3H8. Focus in on the one in the middle. Try the 2n first. 2 times 3, well, that would be 6. If this number here is equal to that, then you know it's an alkene. If it ends up being greater than this, as we see in this case, it's an alkane. If it ends up being less than what you calculate, then it's an alkyne. That's another way to approach it. Again, if you want to be safe, just run it through all 3 of these formulas and figure out which one it matches. The one it matches is what it is. We use this in terms of deciding if a compound is saturated or unsaturated. Again, if you're looking at a structural formula, all you're looking at are the bonds in the carbon chain. If all your bonds in the carbon chain are singles, it's an alkane, and it is saturated. Because alkanes are the only saturated hydrocarbons. If you have a double bond in there somewhere, that makes it an alkene. And that would be unsaturated. If it's got a triple bond in it anywhere, that triple bond makes it an alkyne. And again, alkynes are unsaturated. The only saturated hydrocarbons are the alkanes. Now apply that to the general formula idea. That means the only saturated ones have to have the general formula or general pattern that we see in an alkane. They have to be 8CnH2n plus 2. If they don't fit that, they're not alkanes and they're not saturated. So if you're looking at a set of formulas, and you're trying to figure out if these are alkanes, alkenes, or alkynes, what you're really trying to figure out is the whole thing. CnH2n plus 2, CnH2n, CnH2n minus 2. If what you're asked for is it saturated or not, this is the only thing that matters. So take this number and do the 2n plus 2. That is not a match. So this is unsaturated. Again, take this number and do the 2n plus 2. That's a match. It's saturated. Again, take the number, do the 2n plus 2. Not a match. It's unsaturated. If I give you the formula and I ask you alkane, alkene, alkyne, then you have to consider all three. Is it H2n plus 2? Is it H2n? Is it H2n minus 2? You have to look specifically at which one it matches. If all I'm asking you is this saturated or not, then it's just a matter of seeing if it's an alkane. Do the 2n plus 2 and see if you have a match. If you have a match, it's saturated. If you don't have a match, it's unsaturated. And it really doesn't matter what kind it is. Moving on into the nomenclature. If I give you a structure and ask you to name it, and it's a straight chain, what we have to do is describe the length of that chain and the bonding that's in it. Now the length of the chain will be covered with the prefixes that I gave you in class. Monometh is 1, eth is 2, prop is 3, but is 4, pent for 5, hex is 6, hept 7, oct is 8, non is 9, and zec is 10. The length of the chain will be one of those prefixes. So we have 1, 2, 3, 4, 5. Pent is part of that name. And again, that's just telling us how many of the carbon atoms are there in the chain. The second half of the name tells us the bonding. All single bonds is an alkane, and the name will end in A and E. A double bond makes it an alkene, and the name will end in E and E. A triple is an alkyne, and the name will end in Y and E. This has the double bond in it. That makes it an alkene, so it ends in E and E. So this is something pentene. The last part, and this only applies to alkenes and alkynes, is to say where the double or triple bond is. This gets a little tricky. We only put that location in there if there are 4 or more carbons. If you have 2 or 3 carbons, it doesn't matter, because we're only dealing with one multiple bond, and we don't have to say what the location is, because no matter where we put the double bond, it's the same thing. This only happens when you have 4 or more carbons in the chain. We have to indicate the location of the carbon by numbering the carbons. We start at the end closest to the multiple bonds. We start numbering on this end. That's carbon 1, that's carbon 2. We need to say the double bond starts with carbon 2, so we stick a 2 out in front of the name. Again, this is only when you have 4 or more carbons in an alkene or an alkyne. Alkanes never have numbers. 2 and 3 carbon alkenes and alkynes never have numbers. This is only if you have 4 or more carbons. The other way we're doing this is drawing the structure from the name. And that's just interpreting what the name says. Non is 9. It's a 9 carbon chain. Y&E means triple bond. The 4 tells us it starts on the 4th carbon. So start with the carbon chain. And go ahead and just single bond it together for now, because everything that's not the double or the triple is going to be single anyway. Then go into the 4th carbon and add your triple bond. So 1, 2, 3, 4, add your triple. Now go back and add in all your hydrogens. Every carbon has to have 4 bonds. This one only has 1, so it needs 3 more. This one has 2, so it needs 2 more. This one has 2, so it needs 2 more. This one already has 3. 1 here, 3 here. This one already has 3. 3 here, 1 there. This one has 2. Needs 2 more. This one has 2. Needs 2 more. This one has 2. Needs 2 more. This one has 1. Needs 3 more. So again, interpret the name. Draw out the number of carbons, then go back in and add your doubles or triple bonds to it. For the branched ones, same story, but we're going to have a little bit more information in that name. All of our parent chains will be alkanes, and the parent chain is the second part. Start with that. Pent means 5, ane means single bonds. Again, there'll be no doubles or triples to draw in the branched ones because we're not going to get that far. So go ahead and draw in your parent chain. Start at the end. Then address the branch. This says on the 2nd carbon, draw a 1 carbon branch. So on the 2nd carbon, draw a 1 carbon branch. And then again, go back in and add your hydrogens. 1 bond there needs 3 more. 3 bonds here needs 1 more. 2 bonds here needs 2 more. 2 bonds here needs 2 more. 1 bond here needs 3 more. Don't forget your branch. 1 carbon here. 1 branch, 1 bond, needs 3 more hydrogens. As far as the naming is concerned, when you're working the name out, start with the branch. Don't work it backwards. So if I want to name this, I have to start with the branch. Now this is where most people make their mistakes. The parent chain is the longest continuous chain of carbons. And again, I told you in class, I'm not going to try to mess you up by making the parent chains bent. They will be the straight one. The branch is what connects to it. This carbon here is part of the parent chain. It is not part of the branch. So we have a 1 carbon branch attached to the 2nd carbon. 2 for the location. It's on the 2nd carbon. And it doesn't matter which end we do it on this one. We want to make sure we always have the lowest number. So start at the end closest to the branch. On the second carbon, we have a 1-carbon branch. The prefix for 1 is meth. Put YL on it to indicate that you're talking about the branch. 2-methyl. Now describe the parent chain. Prop is the prefix for 3. They are single bonded, so it's an alkane. So propane is the name of the parent chain. 2-methylpropane will be the name of that compound. We talked about substitutions. Now, what are we going to do with substitutions? I honestly don't know yet. I haven't written the test up. One of the things I might do is just ask you to identify them. So you'll see a mess of structural formulas, perhaps. And I'll ask you to identify what they are from that list of substitutions that we talked about. So expect to see a bunch of structural formulas labeled A, B, C, D, just like it was on the quiz that we took yesterday. And I might ask you which of the above structures is an aldehyde, and your answer would be this one right here. Because aldehydes have that carbonyl group, that double bonded oxygen, and it's somewhere in the chain, not on the end. Actually, it's the ketone. The ketone, the double bonded oxygen inside the chain. I might ask you which one's the alcohol, and that's this one. It's got the OH group on it. Might ask you which one's the organic acid. That's this one. It's got that carboxyl group on it. It's got the OH and the double bonded oxygen, the hydroxyl and the carbonyl attached to it. I'm going to ask which one's the amine, and that would be this one with the nitrogen group bonded to 3 other atoms. So again, it's probably going to be more of a recognition kind of thing, and that's why I said to make sure that you get some drawings in that table so that you know kind of what they look like. Know what the substitution is. In some cases, that's all you need to know, like with the alcohols and the OHs. Sometimes you need to understand where it is too, like with the ketones and the aldehydes. And this one's a mid-chain substitution, so that actually makes it a ketone. It'll be that recognition kind of thing. I may ask you, draw an alcohol and not be specific. And again, like I told you in class, you can take any hydrocarbon. Doesn't matter how long it is, doesn't matter how short it is. You can take any hydrocarbon, pop a hydrogen off of it, put an OH in its place, and you've got an alcohol. That's all you got to do. I might say draw a halocarbon, any halocarbon. And again, just take any hydrocarbon. Take a hydrogen off of it and stick a halogen on it, and you've got a halocarbon. I might say draw an aldehyde. And if I say draw an aldehyde, again, just take any hydrocarbon, and on the end of it, stick the double bonded oxygen. If I say draw a ketone, put the double bonded oxygen in the middle. Again, that's why it's so important to have examples for these things in your notes. We talked a little bit about isomers. Again, I might ask you to identify isomers. As I mentioned, they have the same molecular formula. So, this and this are isomers. And the way you would identify both of those as being isomers is by doing the molecular formula. This is C4, H, 1, 2, 3, 4, 5, 6, 7, 8. Count the carbons, that is C4, H, 1, 2, 3, 4, 5, 6, 7, 8. They both have the same molecular formula but different structures. This is what makes them isomers. Now do remember, isomerism starts with 4 carbons, with the alkenes and the alkynes. So you've got to have the 4 carbons before you start talking about isomers. When you're dealing with 3 carbon chains, this and this are the same. So there really are no isomers in their simplest terms anyways in this. Those are the same thing. The second one's just the top molecule flipped over. So watch out for that. That's again why we don't use those numbers when we're doing the nomenclature. And I think that covers pretty much everything. I might have left something out. If I did, ask me in person and we'll go from there.